Welcome to this video. Today we're going to dive into dimensional analysis. Dimensional analysis is an extremely interesting mathematical tool that allows us to make predictions of formulas based on educated guesses about the physical phenomena we try to understand. This essentially means uncovering the relations between the variables that govern the physical phenomena of interest. I will cover some basics of the method and give various examples, including some exercises for you to practice. Feel free to pause at any point if you need to digest what you see, and keep a notebook handy if you want to try and solve the exercises. The solutions will be provided at the end of the video. So let's have some fun! So what is dimensional analysis? In the International System of Units, also known as SI, we define 7 base dimensions, namely time, length, mass, electric current, temperature, amount of a substance, and luminous intensity. In this way, the dimension of a physical quantity Q, denoted either as dim Q or Q within square brackets, is defined as the product of the base dimensions raised to some arbitrary powers a through g. If only b is non-zero, then we have a geometric quantity, since there is a dependency only on length. If b and a are non-zero, then we have a kinematic quantity, since there is a dependency on both length and time. If a, b, and c are non-zero, then we have a dynamic quantity, since there is dependency on length, mass, and time. Finally, if all powers are zero, then we have a dimensionless quantity. Having covered the absolute basics, let's now move to dimensional homogeneity. When dealing with physical quantities, there are 2 types of quantities to consider: commensurable quantities, which have the same dimensions, and incommensurable quantities, which have different dimensions. Commensurable quantities are those that can be compared, equated, added, or subtracted. Incommensurable quantities, on the other hand, can only be multiplied or divided. For example, let x and y be quantities with a dimension of length, while z is a quantity with a dimension of mass. In this context, x plus y or x minus y are meaningful expressions, since we are adding or subtracting lengths. X plus z or x minus z, however, are not, since we cannot add or subtract lengths and masses. Essentially, this is the apples and oranges saying, but expressed in a purely mathematical representation. On the contrary, expressions like x times z or y divided by z are mathematically perfectly consistent, and therefore allowed. Dimensions essentially describe what a quantity is, its nature if you will. Those 7 SI-based dimensions, however, need to be somehow measured. Therefore, we have defined 7 corresponding SI units. In the actual free world, where we use the metric system, time is measured in seconds, length is measured in meters, mass is measured in kilograms, electric current is measured in amperes, temperature is measured in Kelvin, amount of substance is measured in moles, and luminous intensity is measured in candelas. In this context, base units are those that can't be expressed by any combination of other units. For example, a unit of volume is not a base unit, since it can be expressed in units of length, as volume equals length cubed. Because volume is entirely derived by length, it doesn't need its own independent base unit. And that brings us to unit conversion. We all know that 1 hour equals 3,600 seconds, 1 kilometer equals 1,000 meters, 1 mile equals 1.6 kilometers or 1,600 meters, 1 Kelvin equals minus 272.15 degrees Celsius, and 1 foot equals 30.48 centimeters. Therefore, a conversion factor is used to convert a quantity from one unit to another. For example, let x and y have the dimension of length, but assume that x is 5 kilometers, while y is 2 miles. Therefore, x plus y is meaningless because although we're adding quantities with the same dimension, they are expressed in different units. X plus c times y, with c being 1.6 kilometers per mile, however, is a valid mathematical operation, since we have used the conversion factor c to homologize the units. This is another very important aspect of dimensional homogeneity. What this essentially reveals is that physical laws are true regardless of the units of measurement of the involved quantities, as long as we consistently use the same units for all variables of the same dimension within a given equation. Finally, let's finish with 3 fundamental rules. Dimensions of A equals dimensions of B should always be true, since dimensions should be the same on both sides of an equation in order to be dimensionally homogeneous. Regarding derivatives, when we differentiate a quantity with respect to another quantity, we should always divide with the dimension of the quantity with respect to which the differentiation is performed. In this case, we divide by time. In integrals, however, we do the opposite. Instead of dividing, we multiply with the dimension of the quantity with respect to which the integration is performed. So in this example, we multiply by time. Having understood dimensional homogeneity, let's look at some simple examples. As we all know from common experience, velocity is how length changes with time. Think about the reading on your vehicle's speedometer when traveling at constant speed. It reads, for example, 100 km per hour, which is length divided by time. Similarly, acceleration is how velocity changes with time. When we press the accelerator, the speedometer reading changes from 100 km per hour to 120 km per hour, and since velocity itself changes, acceleration will be length over time squared. The exact same results can also be obtained by taking the time derivative of length for velocity and the time derivative of velocity for acceleration. Or in other words, velocity is the rate of change of length and acceleration is the rate of change of velocity. All these lines of thought are equivalent. Next, let's look at force. Since it is mass times acceleration, the dimensions of force will be mass times length times time to the power of minus 2. Why is force equal to mass times acceleration? Well, remember Newton's second law. F equals m times a. Similarly, if we want to find the dimensions of energy, all we need to do is think of energy as force applied over a distance. So from the previous example, it directly follows that energy will have dimensions of mass times length squared times time to the power of minus 2. Finally, power is by definition the rate of change of energy, so it will be mass times length squared times to the power of minus 3. It is essentially the time derivative of energy. Congratulations! You now know the basic ideas behind dimensional analysis. If you made it to this point, it means I haven't bored you to death, which is encouraging. Now, it's time to put all the pieces together in a more formal way that will allow us to estimate the relations between the variables of various physical phenomena that depend on 3 or 4 variables. So, let's talk a little bit about Rayleigh's method. Named after Lord Rayleigh, the method was developed in the late 19th century in an effort to quickly understand the structure of complex physical phenomena by analyzing the dimensions of the variables involved, even when the full differential equations were too difficult to solve. It is an extremely powerful tool, as will become apparent shortly. The first step of the Rayleigh method is to make an educated guess regarding the variables that likely influence a quantity x. Once we have identified the related variables, we can write x as a function of all the independent variables. We can then rewrite this function as a product of terms, with each variable as a base raised to some arbitrary power. Next, we need to express each variable in its base dimensions, such as length, mass, and time. Now, using the principle of dimensional homogeneity, we can construct a set of equations for our exponents. We solve the resulting equations using basic algebra, and finally we substitute the exponents back to the equation from step 3. Finally, we are now ready to tackle some fun real-world problems. Let's start with aerodynamic drag. Suppose you take your car out for a drive. The car moves with velocity v through a fluid, in this case the air, with density ρ. As the car moves through the air, its forward-facing surfaces push the air away. The equivalent surface that pushes the air is called frontal area. This results in a resistance force that opposes motion. This force is called aerodynamic drag. So what we are looking for is a force. As we have already seen, a force has dimensions of mass times length times time to the power of -2. As is also evident from the sketch we just drew, it will depend on air density, frontal area, and vehicle velocity. Essentially, the drag force will be a function of ρ, v, and a. As per Rayleigh's method, this can be expressed as the product of some constant c times ρ to the power of a times a to the power of b times v to the power of c. We now have our independent variables and the general form of our equation. Our variables have the following dimensions. Density is mass times length to the power of -3, essentially mass over volume. Frontal area has dimensions of length squared, essentially a surface, while v, as we have already seen, has dimensions of length times time to the power of -1. From the principle of dimensional homogeneity, we know that the dimensions of our equation must be the same on both sides. This means mass times length times time to the power of -2 equals some dimensionless constant c times mass times length to the power of -3 all to the power of a times length squared to the power of b times length times time to the power of -1 all to the power of c. We proceed by doing the algebra, expanding the terms and grouping the powers of each base dimension together. The only way for this equation to be true is for the powers of mass on one side to equal the powers of mass on the other side, and similarly for length and time. We now have our system of linear equations. Solving this simple system will provide us with the numerical values for a, b, and c, which in this case are a equals 1, b equals 1, and c equals 2. If we substitute these values into our equation from step 3, we find that the drag force equals some constant c times air density times frontal area times velocity squared. This reveals a very interesting fact. The biggest contributor to the drag force is not how much surface is cutting through the air, nor the air density itself. It is our velocity. Because the velocity dependence is squared, doubling the velocity quadruples the drag resistance we experience. This is the main reason why a 120 horsepower vehicle can easily reach speeds of around 200 km per hour, but in order to reach speeds of 300 km per hour, it would theoretically need more than 400 horsepower, and probably more than 500 horsepower if we account for transmission losses, rolling resistance, and so on. Obviously, frontal area and air density do play a role. This is the reason why land speed record attempts occur in the middle of the day when air density is lowest. It also reveals why high-performance vehicles generally have small, wedge-shaped frontal areas. Frontal area, however, does play a more significant role in motorcycle riding, since the rider's body can move around, constantly changing the effective frontal area. Finally, the constant c essentially incorporates the drag coefficient you may find on any vehicle's spec sheet. A very simple experiment that anyone can perform in order to understand the interplay of these variables with the drag force is to put your hand out of the window of a moving car, first with your fingertips and then with your open palm facing the airstream. You will find that although the drag increases when your palm is facing the airstream at a given speed, it disproportionately increases as the car's speed increases. This allows you to literally feel firsthand the squared velocity dependence influence that physics has just revealed. Now let's move to another example. Assume your adrenaline is running low and you decide to pump it up by jumping off from an airplane, but you have forgotten your parachute. As you fall through the air of density rho, gravity will pull you towards the ground, while the surface area of your body will provide some resistance to slow you down. What will your terminal velocity be? So we are looking for a velocity. Our dependent variable, that is, the left-hand side of our equation, will have dimensions of length times time to the power of -1. Moreover, terminal velocity will be a function of air density, surface area, and the gravitational pull on the mass of your body. As before, we find the dimensions of our independent variables, namely mass times length to the power of -3 for air density, length squared for the surface area, and mass times length times time to the power of -2 for the force that gravity exerts on your body mass. Our equation, therefore, takes the following form. Velocity equals some dimensionless constant c times air density to the power of a times surface area to the power of b times gravitational force to the power of c. Through the principle of dimensional homogeneity, we substitute the dimensions into our equation, we group the powers of each base dimension together, and we construct our set of linear equations. Solving the system of equations reveals that a and b are equal to -1/2, while c equals to 1/2. Plugging the results back into the equation, we find that the terminal velocity depends on air density to the power of -1/2, the surface area to the power of -1/2, and the gravitational force to the power of 1/2. Simply put, it is the square root of your mass times the gravitational acceleration g divided by the air density times the surface area. What is clearly visible now is that the terminal velocity will increase if body mass increases, or if gravitational acceleration increases, or if air density decreases, or if the surface area decreases. For example, if you were to repeat the experiment on Jupiter and assume the same mass, air density, and surface area, your terminal velocity would increase simply because the gravitational pull of Jupiter is much stronger than Earth's. In fact, since Jupiter's gravity is about 2.5 times stronger than Earth's, and the velocity dependence scales as the square root of gravity, your terminal velocity on Jupiter would be roughly 1.6 times faster than it is on Earth. But we can take this one step further. Assume you want to find out what size of parachute would you need in order to achieve a safe landing. Luckily, if we solve the equation we just derived for the surface area, we find that it is equal to mass times gravitational acceleration divided by air density times velocity squared. A parachute, however, can be easily approximated by a semispherical surface, that is 4 times pi times radius squared divided by 2. Substituting this and solving for r, we find that parachute radius is equal to the square root of mass times gravitational acceleration divided by air density times the desired velocity squared. Then, the parachute diameter is simply 2 times its radius. Based on these two examples, can you estimate the escape velocity one would need in order to escape from a spherical body of mass m, let's say a planet? A quick tip: the solution will depend on the gravitational constant g, the mass m, and the radius of the body r. Take your time and apply what you have learned so far. In any case, you can find the solution at the end of the video. Now let's completely shift the tone. We have seen that dimensional analysis can help us find relations between variables in order to constrain physical problems within the realm of classical mechanics. Let's see if the same method has applications also in quantum mechanics, and more specifically, the Planck units. Planck units are the fundamental units used to describe spacetime itself, defining the scales where our current laws of gravity and quantum mechanics meet. They are constructed strictly by using the four fundamental constants of nature, namely the speed of light c, the reduced Planck constant h bar, the gravitational constant g, and the Boltzmann constant kb. The speed of light is essentially velocity, which, as we have already seen, has dimensions of length times time to the power of -1. For the reduced Planck constant, we can find the dimensions using the Heisenberg uncertainty principle, delta x times delta p. This is length times momentum, which is mass times velocity. Therefore, the dimensions are mass times length squared times time to the power of -1. For the dimensions of the gravitational constant, we can look at Newton's law of universal gravitation. By solving for g, we find that the dimensions are mass to the power of -1 times length cubed times time to the power of -2. Finally, for the Boltzmann constant, we can look at the ideal gas law. Solving for kb implies that the dimensions are mass times length squared times time to the power of -2 times temperature to the power of -1. Now that we have our building blocks of fundamental physical constants, let's try to figure out the Planck units, namely the Planck length, the Planck time, the Planck mass, and the Planck temperature, using Rayleigh's method. This is actually much simpler than the previous examples, because we do not have to guess the variables. We already know them. It will be some combination of c, h bar, g, and kb. The only true question is, what is the respective power to which each variable has to be raised? This will be determined by the dimensions of the respective quantity on the left-hand side of the equation. To make this clearer, let's try to figure out the Planck length. Since we want our Planck units to be solely a function of the most basic physical constants, the Planck length is expected to equal the product of the speed of light to the power of a times h bar to the power of b times the gravitational constant to the power of c. Also, the dimensions of Planck length on the left-hand side of our equation will be, well, length. So, substituting the dimensions of the fundamental constants, doing the algebra and rearranging the terms gives us the system of linear equations to solve. Solving the equations, we find that a equals -3/2 and that b and c are equal to 1/2. The Planck constant, therefore, will equal the square root of h bar times g divided by c cubed. Note that c in these examples is the speed of light, not some random constant as in the previous examples. Part of the reason Planck units were introduced was to simplify calculations in theoretical physics. By using Rayleigh's method here, we can set the dimensionless constant c to 1. In this natural unit system, the units are defined entirely by the constants of nature themselves, stripping away any arbitrary human scaling. Plugging the numerical values of c, h bar, and g into the equation reveals that the Planck length is of the order of 10 to the -35 meters. This is an incredibly small length. For context, the Large Hadron Collider in Switzerland, this incredible machine we built to uncover the secrets of the Standard Model, can probe lengths of about 10 to the minus 19 meters. This is a 16 orders of magnitude difference. To wrap your head around this, imagine that you want to understand physical reality at meter scales, but the data resolution limits you to observations on the scale of tens of trillions of kilometers. This should give you a clue about the level of intelligence of the people working at CERN. Now let's attempt to derive the Planck time. The general form of our equation will be exactly the same, although now, since we want to find the Planck time, the left-hand side of our equation will have dimensions of time instead of length. Again, by substituting the dimensions of our fundamental constants, doing the algebra and rearranging the terms, we get the system of linear equations to solve. Solving the equations, we find that a equals minus 5 over 2, and again that b is equal to c, which is equal to 1/2. The Planck time, therefore, will equal the square root of h bar times g divided by c to the power of 5. Plugging the numerical values of c, h bar, and g into the equation reveals that the Planck time is of the order of 10 to the power of minus 44 seconds. The universe at this time is in the Planck epoch. For context, the exponential expansion the universe experienced in its initial stages, which we refer to as the cosmic inflation, happens after the Planck epoch. This should give you an idea of how fundamental the Planck time is. Although cosmic inflation has not been conclusively proven yet, it is very widely accepted at present as being correct, since it is necessary to explain the universe's observed homogeneity. That is, the fact that the universe looks the same at any direction. The primary proponent of the idea is MIT professor Alan Guth. So, can you now derive the Planck mass and the Planck temperature following a similar thought process? A helpful tip is that the Boltzmann constant should appear in any equation involving temperature. Take your time with algebra. Again, the solutions will be at the end of the video. Finally, let's take a look at the Rayleigh-Jeans equation. A great homage, since we are learning today about Rayleigh's method. Let's say that you wake up in the morning and make your favorite coffee. Although you cannot see it, your mug is at some temperature T and it emits thermal radiation. This radiation is called blackbody radiation, and it baffled physicists at the turn of the 20th century. In order to understand how to describe the radiation, we need to understand the concept of spectral energy density. In the framework of classical physics, the spectral energy density of blackbody radiation is a function of the frequency of the radiation, the speed of light with which the radiation travels, and the temperature of the body that emits the radiation. Moreover, since we are dealing with spectral energy density of radiation emitted by a body of volume V, we are essentially dealing with dimensions of energy per unit frequency per unit volume. The dimensions, therefore, are mass times length to the power of minus 1 times time to the power of minus 1. So, now we know the dimensions of the left-hand side of our equation, and we also know that it is a function of frequency, the speed of light, and the temperature. Frequency has dimensions of time to the power of minus 1. The speed of light has dimensions of length times time to the power of minus 1. The temperature, which, as we have already seen previously, goes hand in hand with the Boltzmann constant, has the dimensions of mass times length squared times time to the power of minus 2. But wait a minute, why doesn't temperature have the dimensions of temperature? After all, it is one of the fundamental dimensions of nature, right? True, but recall that the Boltzmann constant also has a dependence on the dimension of temperature to the power of -1, and when taking the product kB times T, the temperature dimensions cancel each other out. Our equation therefore becomes spectral energy density equals some dimensionless constant C1 times frequency to the power of A times the speed of light to the power of B times the product of the Boltzmann constant and the temperature all raised to the power of C. Substituting the dimensions into both sides of the equation, doing the algebra, and solving the system of linear equations, we find that A equals 2, B equals -3, and C equals 1. Putting everything back together, we find that the spectral energy density equals C1 times frequency to the power of 2 times kB times T divided by the speed of light cubed. We have just derived the classical prediction for blackbody radiation. Here is the fun bit. The experimental data suggested that the blackbody radiation energy density should rise up to a turnover frequency and then drop. Our equation, on the other hand, suggests that the energy density should monotonically rise to infinity as the frequency increases. This revealed a great mismatch between the established classical theory and experiment. This became known as the ultraviolet catastrophe. It was one of the major clues that pointed the great scientific minds at the turn of the 20th century to the idea that the classical physics framework did not provide the complete picture of physical reality. We needed new physics, and that new physics was quantum mechanics. So that was it. To recap, we have seen the basics of the mathematical method of dimensional analysis. Here are some pros and cons of the method. Dimensional analysis is excellent for equation validation, quickly estimating relationships between variables of complex physical phenomena, and also allows for conversion between units. Dimensional analysis, however, is not going to provide dimensionless constants. This can only be determined experimentally, provided we already have the general form of the equation. It won't work with equations that involve addition, subtraction, or complex functions like trigonometric, logarithmic, etc. It does not guarantee physical correctness, it only guarantees dimensional consistency. Finally, it cannot distinguish between quantities of the same dimension, for example, work and torque. Overall, although the method has its limitations, it remains a very powerful mathematical tool that physicists and engineers still frequently use. Rayleigh's method is a great tool for phenomena involving up to 3 or 4 variables. For even more complex phenomena involving more variables, you need to dive deeper into the Buckingham pi theorem, essentially a more formal generalization of Rayleigh's method. If you feel that you learned something useful here today, please like the video and subscribe to my channel, as this helps me a lot. Thanks very much for watching. Till next time, have fun!